Get ready for a breakthrough. A novel intelligent hybrid reinforcement learning framework for autonomous decision-making in complex health cognitive systems is here. Researchers have developed a brain-inspired framework that integrates model-based planning and model-free reflexes using a dynamic metacontroller and neuro-symbolic clinical knowledge to revolutionize patient-centric autonomous decision-making.
Here's a simple way to protect your phone without stress. This ALEN 3-pack comes with tempered glass screen protectors, camera lens protectors, and an installation frame for an easier, cleaner fit. It's clear, case-friendly, and built to help guard against scratches and everyday bumps. Check the link in the comments to get it on Amazon.
Next up, we dive into the future of military technology. Experts are rethinking human-machine interaction and the governance of AI in the military domain, exploring what human control truly means across the entire AI lifecycle and offering critical recommendations to safeguard human responsibility. In health tech news, the UK National Screening Committee is consulting on the use of artificial intelligence in the diabetic eye screening program, as they review new evidence on automated grading systems and seek public feedback on the future of AI in NHS services. And finally, we look at cutting-edge hardware. Strategies for high-accuracy memristor-based analog computing and memory are showing revolutionary gains in energy efficiency for artificial intelligence, pushing the boundaries of what AI can achieve. Stay with us for more. A groundbreaking neuro-inspired hybrid reinforcement learning framework has been developed to enhance autonomous decision-making in complex health cognitive systems, addressing critical limitations in existing reinforcement learning approaches for dynamic healthcare environments. Published in Nature Scientific Reports, the research introduces a sophisticated architecture that synergistically integrates model-based, MB, planning and model-free, MF, reflexes, guided by a dynamic metacontroller, neuro-symbolic clinical knowledge, counterfactual reasoning, and robust ethical safeguards. The core challenge in applying traditional reinforcement learning, RL, to safety-critical healthcare is balancing real-time decision-making with adaptive learning amidst high-dimensional sensory inputs, sparse rewards, and stringent safety constraints. This new framework draws inspiration from cognitive neuroscience, specifically dual-process theories, suggesting a collaboration between a slow, deliberative, model-based system and a quick, habitual, model-free system, mirroring brain functions like the prefrontal cortex and the basal ganglia. The proposed framework features a dynamic metacontrol mechanism that dynamically allocates computational resources between MB and MF subsystems, enabling real-time switching based on uncertainty. This metacontrol leverages hippocampal-inspired signals to arbitrate between planning and reflexive actions, significantly increasing sample efficiency by 50% and achieving 95% convergence to optimal reward in sparse reward cerebral palsy, CP, rehabilitation tasks. Key innovations include 1. Neuro-symbolic integration, merging deep neural policies with symbolic clinical information, such as ICD-10 codes and WHO guidelines, to ensure decisions are both flexible and highly explainable, achieving 99.2% globally explainable decisions. 2. Counterfactual reasoning, implementing a module that simulates what-if scenarios using the internal model to assess alternative action sequences, which has been shown to decrease exploration regret and improve safety in edge scenarios. 3. Ethical adaptability, incorporating mechanisms that enforce compliance with WHO ethical guidelines, ensuring patient-centric behaviors and preventing performance degradation in vulnerable populations. Validation of the framework was rigorous, utilizing NetLogo multi-agent simulations on a multimodal CP dataset of 86 patients, alongside WECA classifiers. The system demonstrated a 99% total reward accumulation, with 98% optimal reward in 95% of training episodes, showing a 60% MB/40% MF contribution. External zero-shot validation across 3 public datasets, NTNUHAR children, EGEMG exoskeleton, D4RL, confirmed the framework's generalizability, achieving a macro F1 score of 84.3% and an accuracy of 81.7%. The framework's interpretability is exceptionally high, yielding 99.8% local explanations, with feature importance highlighting critical signals like heart rate and facial expressions as key intervention drivers. Furthermore, the system maintained resilience to noise, demonstrating robustness under 20% environmental variation and achieving a real-time decision latency of 150 ms on embedded hardware. This work successfully bridges the gap between computational rigor and accountability in clinical decision-making, offering a reliable, explainable, and simulation-validated solution for patient-centric autonomous care. A new perspective is emerging on the governance of artificial intelligence in the military domain, centering on the critical principle of human control. The article, published in Nature Machine Intelligence, examines what human control truly entails by analyzing the diverse forms of human-machine interaction throughout the entire AI lifecycle, from research and development to testing, evaluation, validation, and verification. The research explores how interactions at each stage impact human oversight, using potential applications, such as AI-based decision support systems for international humanitarian law assessments, as a case study. The authors argue that these dynamics demand greater attention to uphold human control and propose 3 key recommendations to strengthen this principle. These recommendations include establishing contestation mechanisms to allow humans to cross-check and validate AI-generated information, implementing continuous training programs to equip users to navigate unexpected scenarios lacking sufficient data, and mandating thorough documentation. The paper draws on a broad body of literature spanning international law, military technology, cognitive science, and the ethics of AI, referencing works on autonomous weapon systems, algorithmic bias, and the legal framework surrounding human agency in armed conflict. It addresses significant concerns regarding algorithmic bias in military AI, the black box problem, and the complex relationship between human decision-making and intelligent systems in defense applications. The findings aim to provide actionable insights for policymakers and developers seeking to ensure responsible and accountable deployment of military AI. The UK National Screening Committee, or UK-NSC, has launched a consultation seeking feedback on new evidence concerning the use of artificial intelligence for automated grading within the Diabetic Eye Screening (DES) program. This initiative follows a comprehensive review of the topic, which began in 2021 to evaluate automated retinal image analysis systems, or ARIASs. Previously, the 2021 review concluded that while ARIASs showed promise, the existing evidence base was insufficient to recommend widespread implementation at that time. Following a resubmission of the topic in 2024, a new evidence summary was commissioned to review literature published since the initial assessment. The latest review suggests that some ARIAS systems perform comparably to human graders and could be trialed in real-world NHS services. This testing would allow for crucial data collection regarding the impact of ARIAS on patients, staff, and costs. The UK NSC is now soliciting input from stakeholders and the public on these new evidence findings and conclusions. Responses will be collated and reviewed before the UK NSC formulates an updated recommendation. Diabetic retinopathy, a serious complication of diabetes affecting the retina, requires early detection to prevent vision loss. In the UK, individuals aged 12 and over with diabetes receive regular eye screenings where trained staff assess retinal images. This process relies on primary graders, with second and third graders providing reviews for complex cases, a process that places a significant workload on the NHS DES program. ARIAS are software tools designed to use AI to grade patient images at the level of a primary grader. Since the 2025 evidence summary, new research has been published, including studies comparing ARIAS performance against human graders in detecting diabetic eye disease, as well as research examining the effects of ARIAS use on patients and staff. However, a noted gap remains. No new UK-based studies have assessed the value for money of these systems. Stakeholders can participate in the consultation by downloading the documents from the UK NSC's Diabetic Retinopathy Recommendation page and submitting comments by the deadline of 11:59 p.m. BST on Monday, 3 August 2026. A new review in Nature details the critical challenges and advanced strategies for achieving high accuracy in memristor-based analog computing in memory, CIM, for artificial intelligence applications. While CIM promises revolutionary gains in energy efficiency and computational power for data-intensive AI tasks, it is currently hampered by inherent noise sensitivity in analog computing and non-ideal device characteristics, leading to computing errors. The review systematically dissects error sources across the entire CIM hierarchy, spanning from the memristor device and array level up to system architecture and algorithm design. It examines various mitigation strategies, including material and device innovations, array-level techniques, and algorithm architecture co-design frameworks aimed at minimizing these errors. The authors emphasize the crucial trade-off between computing accuracy and implementation cost, ultimately charting a roadmap for transitioning memristor-based analog CIM technology from early-stage prototypes to large-scale deployment in next-generation AI systems. Key advancements discussed include improvements in resistive random access memory, RRAM, reliability, such as enhancing endurance, improving state stability, and controlling variability through techniques like localized VO formation and optimized programming schemes. Research highlights the development of high-density, high-performance compute-in-memory chips, demonstrating capabilities like achieving high TOPS W metrics and integrating hybrid analog-digital processing. The paper synthesizes findings from numerous related works, showcasing progress in areas such as fully hardware-implemented memristor convolutional neural networks, analog-type resistive switching devices for neuromorphic computing, and the integration of memristors with CMOS for edge AI processors. By addressing the complexities of device physics, array design, and algorithmic co-optimization, this work provides essential insights for overcoming current limitations and unlocking the full potential of memristor-based analog computing for accelerating future artificial intelligence.